Good afternoon, and welcome to this second recorded lecture in the Algorithmic problem-solving course. Today, I will be talking about strings, the second part of strings. So today I will be talking about suffix tree, and suffix arrays, which are all very useful to find different types of string matching problems. So first of all, just to repeat what a suffix is. So basically a suffix is something at the end of a word. So if we have a word like kara, then all the suffixes of kara, ara, r, and a. So those are the four suffixes. And we can also recall from the previous lecture when we talked about tries, which was basically a way of representing a dictionary of different strings in a compact form and be able to find all these keys in a fast manner. So what we're interested here is now to build what we call a suffix trie, which is a trie built of all the suffixes of a set of strings. So for example, if we have the strings car, cat, and rat, then all the suffixes of these three words are car, r, cat, at, t, rat, at, and t. And if we then sort these suffixes and remove duplicates, we get a list of 7 different suffixes. And now we can build a trie based on these, just using the same way as we done before. So basically starting with the first letter, so all the words starting with A share the first edge. So all the words starting with A follow this link, and then we have two options. Either we will continue with an R, continue with an T. When we come to car and cat, we see that they share the first two letters and then they differ. So we can simply build this trie. If we now have this trie, so we built a trie of a given string S, then we can do a number of things. First of all, we can check whether S is a substring of T. So basically now we just have to follow the path from S from the root. And if you finish S while you still have a path to follow, then you know that it's a substring. So for example, A or CA. CA would be a good example. So if we want to check if CA is a substring of any of the words here, we can see that CA is a substring because we have exhausted CA before we have reached the end of the trie. We can also check if S is a suffix. So for example, CA is not a suffix, but rather car or cat or at and so on are suffixes. So in this case, we have to follow the word and end up in a leaf node in order for it to actually be a suffix. And maybe more interesting is that we can also count the number of occurrences of a particular string S in this trie. And basically, it's all about counting the number of paths that leads to leaf nodes. So for example, we can check that the string A is part of two different strings, both car and cat, and then we just follow A here and then count the number of leaf nodes underneath. So then we get 2. Here is another example that we will build on throughout the lecture. So in this case, we have building the suffix trie for the string gata gakaka. Funny word. So here we have all the 9 suffixes if we include empty suffix. And here we have the suffix trie built from these strings. Now what we can do is to transform this trie into a tree. So basically we need to compact all the edges so that we merge all vertices with only one child, and then we put the path labels on these vertices, the internal vertices. So now we get a much more compact representation of the same information. So basically we have merged a number of many different nodes here. If we now have built this suffix tree, we can now find all the occurrences of a pattern P of length M in the string or the tree T of length M. So basically what we need to do is that we need to find the vertex X in the suffix tree, which represents the pattern P. And then we know that all the leaves in the subtree rooted at X are the occurrences. So basically all the way to extend the pattern as a suffix. These are all the places where it will occur. So if we now have the suffix tree as we built in the previous example, we can now see that this pattern A, to find all the occurrences, we just follow the edge A here, and all the leaves in the subtree are then the occurrences. So basically, it will then occur in ata, gaka, agaka, akka, and then A. So those are the four examples here. So we can find all those occurrences. If we take, for example, the pattern GA instead, we again follow the string GA, and now we see that we have two different leaves in the subtree, namely gakka and gataka gakka, or something like that. You get the idea. And we can also see that we have a pattern like Z. There is no path from the root to Z, so therefore it's not a pattern in this. So we can do this very efficiently, namely in order m plus m order m plus the number of occurrences of the pattern as the time complexity. We can also use the suffix tree to find the longest repeated substring. And in this case, it's all about finding the deepest internal node. And then we can see the length of this, the path to this internal node. That is the length of the longest repeated substring. So in this particular case, we actually have two internal vertices. So we have A and we have GA. And since GA is longer, we know that that is the longest repeated substring, and we can also verify that GA is actually occurring twice. We can also use this to find the longest common substring. So actually this is an interesting, because this problem was conjectured in 1970 by Donald Knuth, that there would be no linear time algorithm to solving this problem. But now we know that it's actually possible to do it. Basically, you do that by building the generalized suffix tree for the two strings, T1 and T2. So basically, we build a suffix tree that contains this combined string. And now we can, now we have an example here where we have gata gakaka as before, and we have the second string kata. And now we have to have different ending characters here, and then we build a joint suffix tree containing both these strings. And again, we now can find the internal vertices, and in this case there are 5, which all represent suffixes from both strings. So for example, we know that TA is contained in both, GA is contained in both, CA is contained in both, A is contained in both, and ATA is also contained in both. So this is an extremely efficient way of finding the longest common substring. Namely, in this case, it's to find the deepest, again, it's to find the deepest internal node, which means ATA, this one. So very nice property of this. The challenge is that to build these suffix trees is actually quite complicated. So I encourage you to look up and try to understand the way to build these suffix trees. But for all purposes, you usually do not need to build the suffix trees. Instead, you will build something called a suffix array, which is a simpler form. So it's basically a sorted array of all the suffixes of a string. And it can do most things that suffix trees can. And in fact, it's actually more space efficient and much, much easier to implement. So for this course, suffix arrays should be sufficient for your needs. So let's look at then at suffix arrays. So the first is that we start by taking all the suffixes and sort them. So if we sort, we have numbered the suffixes as before, and then we sort them. So now we get both the kind of sorted index and the actual suffix array position here. So here we see that the empty string is the first in the suffix array, even though it has the highest suffix array number. So we have just sorted them. So now the question is, how do you actually achieve this? Well, of course, you can do this in a naive way. You basically generate all the n squared possible suffixes, and then you, all the n suffixes, and then you sort them in n log n time. And then this would achieve a n squared log n implementation, but can actually do better. We can, for example, push in the log factor by, instead of considering the full strings, we split up the strings in n-grams. And an n-gram is a n-sized consecutive part of the original string. So examples of 2 grams of the string ABBA would be AB, BB, and BA. So basically all the consecutive 2 letters in that word. And for ABBA, the only 4 gram is ABBA itself. And then what we can do is that we can sort first the 2 grams, and then the 4 grams, then the 8 grams, etc. Which means that we only need log 2 iterations instead of n iterations. So that's why we remove the n factor and replace it by log n factor instead. And the way that we do that is to use something called lexicographic renaming, which is basically that we start by sorting all the bigrams or 2 grams, and then we have this list, and if they are the same, we can just keep the number, and only if they change, we update the number. So after going through these in linear order then, we have then ranked all these 2 grams. Now we can use these 2 grams and combine them into 4 grams, basically generating for all 4 grams, which has the same initial part. They will of course have the same number for the first 2 gram. They're already sorted, so only need to sort the second 2 or the second 2 gram or bigram in the 4 gram, and that we can do using the same table that we already have. So therefore, this is a very efficient way of generating all these sorted strings. So actually, we can make this even faster, and then we do the exact same thing, but we actually use radix sort, because now we know the maximum length of the strings, so we can actually do radix sort. But we can do the same as before using quicksort, which is efficient enough for the purposes of this course. And if you actually want the straight linear implementation, I recommend that you look up Ukkonen's algorithm from 1995. And if you want a challenge, why not implement it yourself? So now that we have given an intuition on how to create these suffix arrays, now let's see how we can do these different things using these suffix arrays. So first, of course, we want to find all the occurrences of a pattern P in GA. If we want to find all occurrences of a pattern in a string, for example, finding all the occurrences of GA in the string gata gaka. I cannot pronounce this. Anyway, what we need to do is to do 2 binary searches. The first binary search is to see where in this sorted suffix array it starts. So we have to do 1 binary search and find out where it starts. So we find the first occurrences, and then we have to do a second binary search, finding the last occurrences. And then we find the two different occurrences, and we can just count the number of occurrences in between the lower bound and the upper bound. In this case, it's just 2. So we have found the 2 occurrences of this pattern in this string. So we can do that very efficiently. The second is that we want to find the longest repeated substring. So what we do here is that we compute the longest common pattern array. So basically, we just check if the previous is a prefix. So in this case, A is a prefix here, and here we have the longest prefix of these two is still 1. The longest prefix between these two is still 1, and the longest prefix here is 0, and here again it's 0. And then we come here and we see that the longest common prefix of these is 2, so it's the GA. And then we can just continue, and then we have, in this case, we have found the longest repeated substring, which is GA. And then we have the problem of finding the longest common substring. So again, we do as we did with the suffix trees. We take the 2 strings that we want to find the longest common substring between. We concatenate them, and then we build a suffix array from this concatenated string. And again, we compute the longest common prefix between each pair of elements in the array, but with one difference, is that we keep track of which string we are currently in. So, and then we want to find the longest common prefix, which is between 2 different strings. So in this case, we have the 2 strings 1 and 2. So what we can see here is that here we have the first case. So we're going from string 2 to string 1, and we're finding 1 common. So this means that A is 1 common substring between these 2. And then we have 1, 1, 1. And then we come down here to ATA. So this one is from string 2, and this is from string 1. The longest common prefix is 3. And this is actually the longest common substring between these 2 strings. So we can do this in order and time, which is very efficient. So in this short lecture, I've been talking about suffix trees, and suffix arrays, and how to use this for a variety of different string matching problems. So basically, suffix arrays basically is a generalization of all the different string matching problems that you will encounter in this course. So if you implement the suffix array efficiently enough, you will be able to solve all the string matching problems in Lab 3. Okay, thank you very much. Bye-bye.